Center.
Good afternoon, may I have your ID number? Good afternoon, may I have your ID number?
Technical training courses at its headquarters in Research Triangle Park, North Carolina, and other regional locations across the country. With world-class instruction and laboratories containing equipment donated by leading
Listen-only mode. You may ask questions via the internet using your keyboard at any time during the presentation. However, the presenter may decide to wait to answer your question until the next Q&A session. If you have audio difficulties, press star 0. Questions may be asked via your telephone line. Press the star 1 key on your telephone keypad to ask a question. If there are no other callers on the line, the operator will announce your name and affiliation to the audience and then ask for your question. If other participants are asking questions, you will be placed into a queue until you are first in line. While in the queue, you will be in a listen-only mode until the operator indicates that your phone has been activated. The operator will announce your name and affiliation and then ask for your question. We will now begin today's seminar with a brief introduction of our speaker, Mr. Gerald Wilbanks. Gerald Wilbanks, P.E., is Vice President of Documentation and Engineering Services, DES, in Birmingham, Alabama, and has over 40 years of experience in control systems, engineering, personnel management, quality systems consulting, and instrumentation design in heavy industry. His experience includes the chemical, pulp and paper, power, and manufacturing fields. Prior to forming DES, he was associated with Rust Engineering and Union Carbide. He's a registered professional engineer in 4 states, a member of NSPE ASQ, and an international former president in 1995 of the International Society of Automation, ISA. Gerald is a graduate of Mississippi State University with a bachelor's degree in electrical engineering and was recognized as the Engineer of the Year in 1991 by the Engineering Council of Birmingham. He is a Distinguished Engineering Fellow of MSU and is a Life Fellow member of ISA. He has served as an instructor in many courses, seminars, and other educational sessions for ISA and his own business. And now, Mr. Wilbanks, you may begin.
Thank you very much, Alicia, and greetings and welcome to everyone in this second seminar in our 6-part series dealing with a review of materials for the Control Systems PE exam. And again, I'd like to welcome each one of you and thank you for taking part and commend you for showing the initiative to study and prepare and see what is involved in the Control Systems Professional Engineer examination. And that's the singular focus of this 6-part seminar series that we are in. The first part we did talk about the background of professional engineering. We talked about how the Control Systems exam came to be. Also discussed the overall specification for this year's exam, and then we discussed some test-taking tips and also looked at some of the standards and codes and regulations that might be involved in that particular exam. So I welcome you again to this one, where we're going to begin our measurement part of the seminar, and also we will also discuss the part of the test that deals with transmission, connections, wiring, things of this kind. We will begin our discussion with measurement requirements and sort of how they are used. Today we'll talk in particular about pressure and the importance of that. Then we'll do some comparison signal types and transmission methods. And these 2 parts would represent perhaps 15% of the total exam that you might see in October. And that time, of course, comes up fast if you're preparing for that, and I assume many of you are in the process of preparing, have a lot of your study materials together, and are beginning to look at what might be involved if you're going to take the exam this year. Some of you, I'm sure, are looking at taking the exam in future years when it's given each October on the last Friday of October of each year. So this could be a preparatory or discussion type activity for you as far as taking these seminars. So again, thank you for taking part, and we certainly want to provide some keys to studying some of the topics that you might emphasize, and also help you to identify some of the areas that you're strong in and perhaps some other areas that you need to do a little bit more study in. So today we're going to begin with part of our measurement activity. The measurement total part of the specification represents 20% of the exam. We're going to talk about just pressure today, and then in the third session, seminar session, we will cover some more of the measurement areas such as flow, level, temperature, and things of this kind. So today we're going to basically begin to put the overall realm of process control together, looking at some of the knowledge, skills, and abilities that you need to have to practice in this field of automation or process control. And we're going to, during the course of the seminar series, we will address all of the areas according to the exam specification. We're going to begin with pressure because it's really the basis of many of our process measurements, and it's a key understanding as we go into some of the other areas that we'll be talking about. So today we want to talk and look at pressure and also transmitters in general. First of all, let's get sort of on the same page, if you will, with respect to what we will be looking at in the seminar series. We have a process that we're dealing with. In the case of a process, we're talking about a set of pumps, tanks, equipment, machinery, conveyors, heat exchangers, or whatever, that different products are put in and different variables are manipulated into the process. And the process by itself does not have any real relationship. In fact, if you could just set it up and walk off and leave it alone and nothing changed, it'd be a wonderful world, but unfortunately, probably in instrumentation, we wouldn't have a job. Unfortunately, or fortunately for us, there's things called disturbances. There's variations in the environment, variations in the inputs, variations in the quality and composition of some of the streams. There's mechanical wear and tear. There's a lot of different disturbances that go on within the process, and therefore we find it necessary to measure and control certain variables such as pressure, level, temperature, speed, composition, all different types of things that we may need to measure because they are a key indication of how our process is doing with respect to the desired set of characteristics that we would like for it to have. So we have to have some sort of a sensor and transmitter that we employ, and that's going to be the subject of this session, partially this session, and also we'll talk some in the third seminar session about how do we measure these variables, how do we get that information into the form of some transmitted signal and take that as a input into some device called a controller, where we compare a set point with the transmitted signal, and by doing so we compare what the process variable is with respect to the desired state of that variable, generate a signal based on the error or deviation between those two, and we'll talk about that later on in the sessions also, out to some final control element, perhaps a control valve, perhaps a variable speed drive, could be some other type of conveyor, start and stopping a motor, or some type of a situation there, but some final control element that, in the case of it, varies some manipulated variable, which is an input to the process and does impact or correct for disturbances that we may have in our process. So just briefly, that's our process control system or loop that we will be discussing during the course of these seminars that we'll be conducting. And what we need to focus on today is really going to be the starting of a control variable. We're going to be looking at that with respect to a overall process and the fact that we're going to transmit a signal through us using some sensor and transmitter to represent that control variable to allow us to have that information or data put into our process control system that we're working with. So that's sort of where we're beginning from today, and we're going to look at transmitters. What is a transmitter? Well, first of all, you could have a lot of different definitions for it, but basically a transmitter or a sensor transmitter is a device that converts some physical process variable that is a characteristic of our process into a electronic, a pneumatic, or a digital, some form of an output that represents that particular variable. As an example, we may have 0 to 100 psig, a pressure situation that we convert to a 4 to 20 milliamps, 315 pounds, or some digital signal that may be going to our control system, which may be unique controllers mounted in a panel or on a wall or something like that, or it may be going into a programmable electronic system such as a PLC, a DCS, or what we now call, I think, programmable automation controllers. But in any event, this intelligence, we do need to get that and be able to apply that intelligence to our control system. It could be a temperature, 50 to 250 degrees Fahrenheit. It could be a level, feet or inches or of level that we have in a tank, a vessel, or storage unit, or it could be flow rate, 0 to 200 gallons per minute, some volumetric flow rate that we have interest to. But what we're doing is getting these into a common output, if you will, from our sensor, from our transmitter. And I will talk a lot using the term 4 to 20 milliamp, 24 volt DC for our electronic units that we're using for transmitters. But again, the output of these devices can be electronic, can be analog electronic, can be digital electronic, it can be pneumatic. These are the standard units ranges that we have now. Sometime back we had pneumatic wars and we had electronic wars, just like we have some of the field bus wars today. But after all the smoke had cleared, the settlement came out at 4 to 20 milliamps or 315 pounds. Of course, now we have digital signals. So what we're doing here is taking a physical process variable, putting that into some form that we can use as the intelligence and data for our control system to affect our process control. And we'll be talking a lot, at least initially, basically, as we looked at on the prior slide, in the form of what we would call regulatory feedback control. This is regulatory feedback control. As we go through the seminars, we will change this somewhat and go to some other time. But this is feedback regulatory control that we will be looking at for the most part. And the sensors that we have, the transmitters, are those devices that give us that intelligence for our control system. So that's how we go about to begin with. And now, talking about transmitters in general, let's look at some terminology that could come into play not only with some of the questions on the exam, but you might have to understand these terms if you to read a question about some other part of the exam, some other topic area in the exam. So we need to have some commonality here. First, we talk many times about an LRV and a URV for a transmitter. The LRV being the lower range value, or the lowest value that measured variable, of that measured variable, that the device is adjusted to measure. And just along the same lines, the upper range value, the URV, is the highest value that the measured variable that a device is adjusted to measure. Now, if we look back at the prior slide that we had, excuse me, I went to go back to this. In that first case, 0 would be the LRV, and 100 would be the URV for the first situation. And if you look at the others, you would see, for instance, 50 to 250 degrees Fahrenheit, 50 would be the LRV, 250 would be the URV, and so on. So we have LRVs and URVs, and when we say LRV, we do not necessarily mean 0. That is the lowest value of the measured variable that the device is going to measure. Then the range, we'll talk about the calibrated range many times, and we say the calibrated range, that's the region between the limits within which a quantity is measured, received, or transmitted, expressed by stating the lower and upper range values. For instance, the calibrated range for that first transmitter, 0 to 100 psig. In the case of the temperature transmitter, it would be 50 to 250 degrees F, or Fahrenheit. So that would be the range. And then if you get a question that refers to what is the span of a transmitter, that is the algebraic difference between the upper and lower range values. So that's simply the span from the lower to the upper, and it's just the algebraic difference because, again, if you go back and you look at these particular situations, this pressure transmitter would have a span of 100 psig. The temperature would have a span of 200 degrees Fahrenheit. The level transmitter might be a span of 120 inches or 10 feet. And same way with the flow measurement, the span would be 200 gallons a minute. Again, is the difference between the upper range value and the lower range value. So you might have questions, or part of the exam might ask you to deal with some of the characteristics of the calibration of the range and the span for a particular measurement device. So we need to understand that. And again, this sort of summarizes some of what we were talking about there. Now let's go over some of that to make sure we have that. The span, as we said, is a singular number that's the algebraic difference between the upper and the lower value. When we talk about zero, that's going to be the true zero value of the process, not necessarily the LRV. It's the true or real zero. The calibrated range, again, 0 to 50, 0 to 100. It's a from and to. The output, then we would get analogous or proportional to that particular calibrated range would be 4 to 20 milliamps, 3 to 15 psi. Could be contact closures, digital outputs. It could come in a lot of different range circumstances there. And then sometimes you'll see them discuss or ask about the linearity of the transmitter. And basically that's the ability for the transmitter to have an equal change in output to an input change, or in other words, if you plotted the output versus the corresponding input that gave that output, it would draw a straight line from 0 to 100% of the input to 0 to 100% of the output. And what happens in reality many times is that line is not exactly linear, and if you check the calibration points at 0, 25%, 50%, 75% on your way to the maximum input, and then come back down while you observe the outputs, you may get what's called a hysteresis, or nonlinear calibration curve. So that term we need to be aware of. And then the base term of accuracy, which is really simply the percent of deviation from the absolute value. So these are some terms that you will see with respect to any kind of a transmitter, regardless of the particular process variable that you're dealing with. Some other terminology that you might see or run into on the exam or in your work is a term called the suppressed zero range. That simply is a range in which the zero value of the measured variable is less than the lower range value. You're looking at true zero and comparing it to the lower range value. If it's less than that, it is a suppressed zero range. And an example here would be if you had a calibration of minus 20 psig to 120 psig, that would have a suppressed zero range because your zero value of your measured variable is actually less than the LRV. Then also you can see some terms sometimes dealing with elevated zero range. And along that similar line, you're comparing the zero value of the measured variable, and see if it is greater than the LRV, we call that an elevated zero range. Now this is strictly, I guess you might say, out of textbook, and if we look at a minus 20 to plus 20, you can see that the true zero is greater than the LRV because the LRV here is actually minus 20. So therefore it's what's referred to as an elevated zero range, and this will have to be taken into account in the calibration procedure for a device be it a conventional analog transmitter or a smart transmitter or whatever type, whatever the calibration process, either electronically or by using a elevation suppression kits on the device, we will have to take that into account. So we need to know that terminology because occasionally it may enter into some of the work or even some of the questions on the exam. Another term you will hear is fairly common is in the overall accuracy. That'll be stated usually in terms of the calibrated span. For instance, plus or minus 0.1% or plus or minus 0.2% of calibrated span. Now that is different. In some cases you could see a device that says the accuracy is plus or minus 1/10 or 0.2 or 1/4% of maximum span. And that would be a completely different situation. So you need to know if it's of calibrated span or is it of maximum span. Typically it's going to be of calibrated span. And if we look at what does the accuracy include, first it has the repeatability. The repeatability is the ability of that transmitter to come back to the same output for the repeating times for a specific input. In other words, if I put 50 inches of water on this differential pressure transmitter today, and I come back tomorrow and do it an hour later, I get the same output. Now the output may not be entirely correct, or may not be entirely accurate, but it will be repeatable. The linearity we talked about, that's the ability to have a equal change in output to an equal change in input, and that can be caused nonlinear, give us some hysteresis on that, and occasionally there could be some deadband, where when you reverse from directions on the input to the transmitter, nothing happens initially. Could have a little deadband, not very much in most of our newer or later electronic transmitters. So that has to do with the performance spec that you might see in different transmitters. Now with that definition and those terms sort of put in place, let's talk about the first measurement area that we're going to look at is pressure. Pressure is such a common term. We will use it both in level measurement, we will encounter it in flow measurements, we will discuss it in control valves, we will discuss it in process data. So we need to understand what is pressure, and the simplest or the simple term for pressure is it's equal to the force per unit area. It's the force that is applied on the area that is available. So that force divided by that area gives you pressure, and our common terms that we'll be dealing with throughout the areas of the class will be PSI, pounds per square inch, or PSI is a very common term, but then we'll also work a good bit with hydrostatic head, which is inches of water for pressure units. Actually, differential pressure measurements of flow will usually are calibrated, those units, in inches of water. We will be using pounds per square inch, or PSI, many times for inlet pressures and outlet pressures, process variables of pressure in pounds per square inch. So pressure is equal to force, in this case pounds per square inch, or actually hydrostatic head, which we will have in many cases, and we refer to that in inches of water for the pressure units. And one of the things in talking to the people that work with the exam is I'm told that some of the major errors take place because of people being inconsistent with their units. Always watch your units on the exam. Always be aware, are you talking about feet or inches or square inches or cubic inches? What type of units are you dealing with, and keep those consistent. And I understand many times problems, which we talked about test taking tips in the first seminar. One of those test taking tips is read. Read the problem carefully. Read the the alternate solutions very carefully and keep in mind exactly what your units are. Please don't mix up units. So I'll mention that. We need to know about that. Okay, a very common term that we will be talking about in the course of these classes will deal with a term called specific gravity. Now that's a reference unitless number, basically comparing the weight of a specific volume, in other words the density, pounds per cubic foot, of a liquid to the same volume of water at 60 degrees F, and the weight of a specific volume of gas at 60 degrees F to the same volume of air at the same temperature. Now, for purposes of reference, and we'll use this in many calculations in many parts of the review, specific gravity of water, since its density is 62.4 pounds per cubic foot, that is set up at 60 degrees F as the specific gravity of 1. So if you have something that weighs more than 62.4 pounds per cubic foot, the specific gravity will be greater than 1. If you have something that weighs less or has a less density, then the specific gravity will be less than 1. For example, let's say that we have a petroleum product, 54.8 pounds per cubic foot, and we're given that on the exam or on a test, and we don't know what specific gravity is. How do we get that? We divide that number by 62.4. In this case, the specific gravity would be 0.88. Many times they will give you the specific gravity. Sometimes you may have to look up the specific gravity. So you need to have some tables, charts that do have some specific gravities. Or if you can find the density or the weight, the specific weight, pounds per cubic foot of that particular liquid, then you can divide by 62.4. Then also, we look at gases. The specific gravity of air is 1. Again, that's the weight in pounds per cubic foot of air at 60 degrees F, and then you'd compare other gases with it. For instance, methane has a density of 0.04243 pounds per cubic foot. Then if I compare that to air and divide that out, I'll get 0.555 as my specific gravity for methane. And so therefore that's a very important factor. And there's another thing that I would like to mention here. Sometimes you might be given the molecular weight of a gas. For instance, maybe you're given the molecular weight as 32 for a particular gas. What does that mean to you? Well, if they give that to you, it could mean, for instance, you need to know that the molecular weight of air in its standard condition happens to be 29 or approximately 29. It's a little bit varied from that, but in this case you would divide the 32 by the 29. In other words, you would divide the molecular weight of your gas by the molecular weight of air. And in this particular case, and I don't have my calculator right here in front of me, but I believe this will give you something like 1.1 for the specific gravity for that particular gas. So you might be given the molecular weight, you might be given the specific gravity, you might be given the density, but in any case, what you're doing is comparing the specific weight or density of the liquid to water, or the specific weight or molecular weight of the gas or vapor to air, to get a dimensionless reference number that tells you the relative weight or specific gravity of that particular fluid. So we need to understand that. Again, that's some units that we need to have in our mind and be aware of what those are. So on pressure, units of measurement, as we said, there's a few that we use as a standard on that, and we need to be aware of those. Pounds per square inch gauge and pounds per square inch absolute. So you will see these terminology, these units, PSIG and PSIA. Well, what do they mean to us? Well, the gauge pressure is reference to atmospheric pressure. We actually compare the pressure that we have in our vessel or in our line to what is the actual atmospheric pressure. And if you look or understand that at sea level, the atmospheric pressure actually is 14.7 psi. In other words, if I go down on the beach near the Gulf or some point, that atmospheric pressure is going to be approximately 14.7. That's psia. Now that is the same as 0 psig. In other words, if I'm standing there holding a pressure gauge in my hand, it reads 0. But actually the pressure, the atmospheric pressure that exists at that point is 14.7 psia. So then if we're given gauge pressure, let's say we're given 50 psig, and our calculation formula calls for the units psia, then we have to add 14.7, or approximately 15, so that 50 psig would be 64.7 psia, or approximately 65 psig. Now, is the atmospheric pressure the same anywhere in the world or any point that you go to? No. It will vary according to what? Well, it will vary according to your altitude. For instance, if I go to Denver, Colorado, approximately a mile or 5,500 feet or something up, that atmospheric pressure that we're talking about here, that atmospheric pressure will be different. I don't know exactly what that is, but I think approximately 12.8, 12.9, perhaps at a mile of elevation. So we would need to use that maybe in some of our calculations, and also keeping in mind that PSI goes down to absolute 0, or the perfect vacuum. So we need to understand these units. We need to know about PSI, pounds per square inch gauge, pounds per square inch absolute, and the fact that we also use inches of water, inches of mercury to display vacuum. A little side note that I sometimes ask people, if you're watching the weather on the news at night and they say that the barometric pressure is 30 inches, what are they saying? And many people don't understand what they're saying there. It's 30 inches of mercury. 1 inch of mercury is approximately 0.49 psi. So 30 inches of mercury is, surprise, 14.7 psia. So again, we're talking about absolute, we're talking about atmospheric pressure. So we need to have those terms in mind, because there will be times on calculations that you will be given gauge or whichever, and you need to be able to go back and forth, and we'll talk about other units later on in temperature and flow, but this is on the pressure part, so we need to be aware of that. So pressure is a very common process variable, or a very common characteristic of a process, of a system that we're dealing with. And how do we measure that in a line or a tank? Well, we don't have time in this particular treatise here that we're dealing with on this seminar, but here's a list of some of the typical sensing elements. For instance, a manometer. A lot of you are familiar with a U-tube manometer that's filled with some liquid. Could be water or some other, but as long as we know the specific gravity and apply pressure to one side of the U-tube, and we reference the atmosphere or another unknown pressure on the other side of the U-tube, the liquid will move in the column and give us how much pressure has been applied to it. A lot of the pressure gauges, field gauges that you see in the field, are either Borden tubes or helicals or capsules of diaphragms, depending upon, is it a high pressure like thousands and thousands of psi, or is it a medium pressure, 100 to 150 pounds, or is it inches of water, something like that. These are used many times in the local pressure gauges that you see throughout industry and throughout different types of different process units. Or it could be really low. We might use a bellows, or there is a differential pressure bellows. We'll also use diaphragms, capsules type, for our primary measurement sensing devices for the transmitters. We use a lot of those, and on those, as those diaphragms have small movements, we will be using either some sort of a strain gauge or a variable capacitor, and as that pressure varies some, it would change the output. And then some devices actually use a linear variable differential transformer, whereas a core sense is moved through a magnetic field. It changes the coupling on the particular transformer, and we get different outputs. So there's a lot of different devices. These are covered in books, and everything that we talk about, there's books written about them basically. And we will be focusing primarily on transmitters, which use some sort of a capsule or a diaphragm. It's a small movement that is obtained by having a pressure on one side and using the plates of the diaphragm as a capacitor, and changing the capacitance as the pressure goes up and it drops off. In fact, all pressure measurements are a differential pressure. You're either comparing a pressure to the atmosphere or atmospheric pressure, or you're comparing a pressure to some unknown pressure, like in a level or a flow measurement or something along that line. So all pressure measurement is actually a differential pressure measurement, and we need to keep that part in mind too. On previous exams, I know I've seen questions that deal with how do you install some of the units and devices that you'll run into. This is a sort of a sketch of different types. For instance, this first one, the instrument's mounted above the process. We have the instrument mounted above the process, and that is really for a purpose of like a gas or a vapor measurement. It would allow any condensables to drain down and back into the process or to the tank. So this would be on gas or vapors, assuming that the temperature or the corrosivity of that measurement is fluid is not detrimental to the transmitter. Okay? If it is detrimental to the transmitter, you would need to revert to some sort of isolation. For instance, here the process is isolated via a sealed pot and a liquid-filled lead going down to the transmitter, and that allows us to seal off from the process to our transmitter if we have some sort of temperature or corrosivity. Also, this type of measure would be used for steam flow, for instance, to isolate the steam vapors from our transmitter so that we did not have to use some unique type of metal constitution on our transmitter. Now, we would also have to be aware, though, that we do have a situation here, depending on the range there, we would have to be aware that that's a liquid-filled leg that our transmitter might be involved with as far as the calibration is concerned. It would depend upon the magnitude of the process pressure. Okay, what about this situation here where we have our process and we mount our transmitter below that particular device? Now again, we're isolated to some degree if we want to put a different fill fluid in, but also we would use this for a liquid situation where we'd have a liquid fill lead, and then any vapors or any gas bubbles that might be produced in that down leg would rise back up and into the process. So again, we could use a different liquid fill for that down leg, or we could use actually the process liquids themselves. But what that allows us to do is any vapors or bubbles formed will rise back up into the process. And this final situation over here, we actually deal with what's called a remote seal and a capillary tubing with our transmitter. And what we effectively are doing here is another form, it's a form of isolation. What we're doing is the process is isolated at this point through the diaphragm seal. So the process is on one side. The other side then is a filled, sealed system, the capillary tubing running back to the transmitter, and therefore none of the process will be, the transmitter will not be exposed to any of the process. And again, you have to take care of the capillary tubing. It's a filled, sealed system. and as I've seen in the field in past times, you don't cut and splice that if you have too much capillary there. But these are a way to isolate the instrument or transmitter from the process to avoid high temperature, avoid corrosive gases or liquids or whatever, to stay away from sludge or slurries, to keep the leads from plugging up. So these are all methods of installation. This is like an installation detail. I just show this to give credibility to the fact that this is on liquid or steam pressure perhaps, and here is our down leg, and our transmitter is effectively isolated from the process. It does have a liquid leg there that will have to be taken into account if it's significant with the range of the transmitter. For instance, if that leg is only a couple of feet and this is in a 800-pound service, it's going to be insignificant. However, if that leg is, say, 4 or 5 feet of liquid, then you'd have to maybe take that into account if the process variable was only 50 psig or something along that line. So that would be a case of your elevation suppression deals, and you'd have to take that into account as you calibrated that particular device. Conversely, on air or gas situation, we show this one here, air or gas, the transmitter is located above the particular connection point to the process, either a line or a vessel, and the condensables will drain back down into the tank. So this would be a way of installing a transmitter, a pressure device, if you will, on a air or gas situation. So you could have questions dealing with how to install a particular device with respect to the kind of fluid that you're measuring. At the same time, and I would count on here, what these little mark numbers are, those are particular items or call-outs for a bill of material, which we're not looking at right now. But D, for instance, might be a half-inch stainless steel tube, and E is a half-inch stainless steel needle valve, etc., etc. So we're not getting into that kind of detail, but I thought I'd mention what those are. So pressure measurement, it covers a lot of ground. It can be accomplished using a lot of different types of devices. Do you need that for local indication only? Is it going to be a transmitter? Is it a gas or a vapor? Is it liquid or steam? Where do I need to mount my transmitter? But also I have to know the conversion factors and units, and we'll be going over some of those as we go along in the measurement part of the seminar series. But the purpose here is for the sensors and transmitters, in this case pressure, to get that data or intelligence back into the receivers and to the control systems. And one thing that I always mention to people, I think is very important, all instruments will work if they are applied properly, installed properly, and maintained properly. And I think that's a key thing that they check you on from a practical standpoint is, do you know how to physically install instruments, valves, things of this nature? So you need to be aware of those and up to date of those. And also, like I mentioned, pressure is a base unit of measurement, but other measurements, base variable, and we need to be aware of those units because we'll be using them as we go along throughout the seminar series. So that's sort of what we covered in this part now, and Alicia, I'll turn this back to you and we'll see if we have any questions. Alicia, do you have any questions? Hearing no questions, then we will move on with the rest of our seminar series today. And we're going to be moving into the signals and transmission part of our situation and talk about how do we get this information back and forth, how do we handle this. This is a part of the specification. If you look at the specification for the exam, you will find that it covers, and I'm looking at the spec right now, pneumatic, electronic, hydraulic, digital, analog buses, transducers, intrinsically safe barriers, grounding, shielding, basic signal circuit design, unit conversions, transmission, different types of protocols, coaxial cable, fiber optics, wireless, etc. So they can cover many different parts in there. We don't have enough time to cover all of that, and some of those considerations, by the way, we will be dealing with later on in some of the future seminar sessions that we will be involved with. So let's move into this part and talk about this to some degree and see if we can get a little bit of an idea of some of the questions that could come up with respect to what we could experience on the examination. Signal types. Right off the bat, of course, we have the analog electronic signal types that we can encounter or get involved with. We'll talk a lot about 40 to 20 milliamps. If you go out in the field at different locations, you may see 10 to 50, which was one of the type that sort of lost out in the milliamp wars. You may see 1 to 5 volts. You may see minus 10 to 10. A lot of different signal levels depending on the type of device and the type of transmitter that you have. So we have to be aware of that, as well as also we can have the analog pneumatics. And pretty much they've settled into 3 to 15 pounds. You will see 6 to 30 psig used in some of the pressure valve situations or circumstances where the control valve has to be controlled by a higher pressure. But this is some of the common ways that we can we see how things settle out, and you can have some different levels. And of course, anytime you go into another operation or another process, you never know exactly what you may run into. But these are some of the common signal levels that you would run into in the analog world. Of course, there's also the digital situations that you can encounter, and different transmitter situations have those. How do we get the information around? Well, in the case of electronic analog, of course, I think all of you are familiar with twisted pair copper cable or twisted pair shielded copper cable. Coaxial is used in many cases for certain benefits that it has, and fiber optics has some advantages and is used in many cases, savings on room and space, etc. But you'll also see multi-cable bundles, and one of the more recent wireless transmission now is becoming more and more ingrained in some of our industrial process units, because there they can take advantage of the circumstances of communicating that around the unit. The security has become much better now, and so wireless transmission, not only for just data acquisition, but even being used for control. So you could have questions that might deal with some of these, and I think you'd be well to review, look up on some of those, and be conversant in different parts of the transmission types. Another thing that I think they will be involved with, and there's, I guess, a multitude of questions that can be generated from these type of topics, practical wiring considerations. And, you know, I think here you need to review probably some of your National Electric Code, and we'll talk later on about wiring considerations in other seminar sessions, like for intrinsically safe and hazardous locations. but general wiring characteristics, for instance, just a few that I thought of that there's always a chance about, like fiber optic cable is very immune from electromagnetic pickup and all. So it's a very good use for that cable where you have areas with a lot of interference that might be involved. Grounding practices. Grounding is very important not only for certain transmitters that we'll talk about later, like magnetic flow transmitters, but also in the cables running back and forth, perhaps from the transmitter to junction boxes or to other marshalling panels and on into the control room. For instance, in a conventional electronic analog, you don't want to ground the transmitter cable at both ends. You'd only want it grounded at one end. If you grounded at both ends, you could set up ground loop circulating current. So you don't want to do that. There could be questions involved about physically how to install some of the cable that you might be running in an industrial plant or any type of a power facility or whatever. For instance, fiber optic cable, one of the major concerns there is you don't want to put it in tight bends because you can break some of the fibers there. So little practical questions like that could enter into it. And I don't know, there could be situations where they might have some questions dealing with how do you install the conduit and cable tray. Of course, that depends on the type of industry and environmental considerations, and so most of the questions they try to have are generic in their structure, and they're not dependent upon industry, but you could have some questions dealing with actually the conduit and cable tray that's involved. So you need to be looking at some of the physical considerations that you might have for general wiring practices, and that's the reason I referred you to the National Electric Code. And then later on, we will deal with intrinsically safe wiring. We will deal with explosion-proof for classified areas or explosive areas, hazardous areas. And all those have specific wiring practices, and we'll talk about those on some of our later seminar sessions. So on the pneumatic type, because, you say, well, we don't do much pneumatic work anymore. Well, that may be true, and it's not in some cases, and the test is probably set up where it covers a little bit of everything, and we need to be aware that pneumatics do exist. We use copper or polyethylene tubing, and many times you're using pneumatic actuated control valves, so you do have pneumatic signals. You do have copper or stainless steel or polyethylene tubing. You do have some characteristics you have to watch, and you're using normally 1/4 inch and smaller to do this, but these also become part of the characteristics, how they react, become part of the characteristics of the overall dynamic response of a control loop, as an example. So we need to be aware of that. And there are multitude bundles that are run many times from the junction boxes back into the control rooms, but also there may be a multitude of pneumatic controls in an area, or you may be involved in a facility that has a lot of pneumatically actuated valves or other types of dampers or drives or whatever. So we have to be aware that pneumatic still exists, is still part of many units, and in fact there's some considerations that we should take into account. For instance, in pneumatics, there will be a time lag. The transmission medium, in this case air, it's a compressible, and there can be a time lag in the signal change from the time that it's called for till it actually takes effect. In fact, tests run on pneumatics indicate that that time lag is going to be like a little dead time plus a first order lag, very similar to many process control loops. And this time lag, or this dead time, can also be a driving function that determines the dynamic characteristics of the control loop that must be taken into account at the time that you're actually tuning the loop or using the loop. And then there are some limitations. For instance, some tests run used 1/4 inch of tubing, 350 foot long. They had a time constant of about 1 second, and actually had a 1/3 second dead time from the time they initiated a pressure change till it was actually received and impacted. So I think it's something that we need to be aware of, that the pneumatics do exist. We wanted to cover that in this section, this part of the seminar. And also, along the line of instrument air quality, I think we need to be aware, and there might be some questions of practical nature dealing with, do we just take any kind of air that we can get, or do we have requirements for that? Well, there are requirements for air quality as dealing with instrumentation or control valves, out-of-peak transducers, pneumatic valve positioners, local pneumatic controllers. There's an ISA standard, I believe it's 7, that establishes a maximum allowable dew point. In other words, dew point is temperature where the vapor, condensate begins to form out of the vapor. And if you have a dew point that's too high and you start forming the vapor, vapor begins to go into a liquid state. As that temperature continues to drop, you can freeze up and have a situation of devices malfunctioning and not working properly. So this one establishes a dew point minimum requirement that says it should be 18 degrees F below the normal minimum expected ambient temperature, or 32 degrees F as a maximum. So if you're working in the Upper Peninsula of Michigan outside, that's one situation. And if you're working in, say, Baton Rouge or Mobile outside, that's another situation. But in any event, you would want to have a dew point that is below your minimum expected temperature. Also, in this same specification, or same standard, the oil content is limited. You want to make sure that you don't have a lot of oil and oil vapor in this instrument air, because the quality considerations will not allow that as they operate with the flapper nozzles and the small movements of tubing and all. So you've got to be sure that you have that limited. Whereas normally you might have a plant air system, say at 100 psi distribution, and it may have oil in it because it's going to be used for jackhammers or other types of pneumatic equipment, and that's okay. But in the instrument air, we don't want to have that, as well as we do not want to have large particulate matter, which will plug up the flapper nozzle areas that we're working with. And also we need to look at other contaminants, and in general, the air source is important and is a consideration on projects or any type of installation, industrial chemical plants, pulp paper mills, power plants, things along that line. So we need to be aware of that, and you need to be aware of the standard and the fact that there is a particular concern about instrument air quality. For instance, here's a sort of a typical instrument air supply system that you might see in certain circumstances where the compressor is used, but we also go through a series of aftercoolers, maybe a separator, air receiver with a drain. We're trying to get liquid out of the air. We're trying to begin to cool that down and get it to a situation that we'll have a dry air. Maybe from that standpoint, it will continue on through some other equipment, pre-filters, drains, dropping the oil and water out, maybe a desiccant air dryer, and only then, after we've gone through that type of preparation, maybe we would check the dew point, and then even after that, there may be some sort of a after filter installed to ensure that we do have good instrument air quality, that the air we're using for our pneumatic devices, be the transmitters, controllers, or valves, will be the type that we would want to have working in our particular plant. Probably this instrument air system will be distributed at anywhere from 35 to 50 psi. Many facilities have a plant air system and then a separate instrument air system that they can take advantage of and that they use as far as their operations are concerned. All right, let's talk a little bit about smart devices, or first on smart transmitters primarily. These have come a long way in the last 15 or 20 years. We still have the same physical plant, you might say, with a device, but that device has the capability of digitizing signals. It has microprocessors, has certain advantages, and certainly the configuration and use of the smart transmitters has really changed the overall process control or automation world as far as our industrial facilities are concerned. As I said, sort of the same physical plant, we still have, in the case we're looking at here, some sort of a control function. In this case, we're showing a single loop digital controller. But the main thing that we've done here now, thanks to the microprocessors, is we can have a smart transmitter, or we can have a smart I2P or smart valve package. And what this basically means is that while we are still involved with a process input that may be differential pressure, temperature, or whatever, and we can still utilize a 40-20 milliamp signal, we also have the capability within that particular device, the smart transmitter, to perform calculations, square root linearization. We can store historical data and curves. We can check calibration and see how things are operating, and even then we can use a handheld communicator back in the control room or at some location to actually communicate with the smart device, rearrange it, check for diagnostics, etc., etc. So there's a lot of advantages, and by the same token, the smart valve packages or smart I2Ps have the same capabilities with the microprocessors, so on and so forth. Smart transmitters have been around. The smart valve packages, the Valtech Star Pack, I think, is one. I'm not sure that's the name anymore, but the Fisher Field View, there's a lot of different packages. So we need to be aware of the smart transmitters, the smart valves. The basic concepts are still the same. Our control function is still the same. We still have our, I guess you'd call it our conventional loop of transmitter, controller, final control element, and we're still looking at processes. We're still looking at variables, but the smart transmitters and the smart valve packages have led to a much better accuracy than we had before. At one point in time, we were using the conventional analog transmitters, actually of 1/4, 3/4%, some of them even 1% in some cases, and we were using those and putting that into a highly accurate electronic computer system or some system that had high accuracy. But now with the smart transmitters, we can get even better than 1/10% of span, which is a lot better than the old 1/4 or 1/2% that we used to get. Some of the other, of course, advantages that we're able to take and use is the linearity, no hysteresis. We can fit curves, we can compensate for temperature. So we got a microprocessor there that we can do a lot of different things, a lot of different types of calculations. We get better rangeability. Now, rangeability is a term that we didn't cover a little earlier, but rangeability is typically defined as the ratio of the maximum upper limit that we can record, that we can measure with the stated accuracy, to the minimum that we can still maintain that same degree of accuracy. So perhaps in some of our older devices, this was more like 3 or 4 or 5 to 1, and now in some cases you get a much higher rangeability between your upper and your lower limits of your spans. So that's very important, and it gives a much more varied results with our transmitters, make them much more flexible, much more usable. And then the reliability has gotten better each year. Really, the mean time between failure, for example, on electronics exceeds 50,000 hours or maybe even more than that. So the reliability is extremely high. That helps out our maintenance. It also helps out in many cases our our safety systems that we're concerned with, because we just have more reliable devices that are able to be used and give us better results. So that's some of the information about transmitters, some of the wiring considerations. Let's go further with wiring considerations, particularly talk a little bit about field bus, a little about how they're installed, a system architecture. We'll brief on this a little bit later on too, but today let's do at least touch on this. For instance, the field bus is a generic name. It's a data highway, and you have various field devices that are hung off of, if you will, this data highway. And this field bus, it's information bused back inside to our control center and back out to our control devices. By doing it this way, there's tremendous potential, reducing the field wiring and input-output hardware cost, and actually going even further with true distributed control using field bus. You have the potential to actually move the move the control functions out to the field devices. Locate that actually in the transmitter, locate that control function actually in that smart valve package. Some people are doing that rather extensively. Others are doing it on a cautious basis, but we need to be aware of that in case some sort of a question did come up. This is just a sort of an indication that I mentioned earlier about there were milliamp wars and there were pneumatic wars, and field bus wars also have taken place. So there's been a lot of modifications, a lot of things introduced. People are settling down to a large extent. There's maybe not a complete standard on the ISA 50 standard, but foundation field bus were introduced at ISA 96, and that's become a major concern, a major player in the field bus war, the foundation field bus. Profibus came out of Germany, World 5th out of France. There's other standards that's being used in certain types of devices. So field bus, you still have to make sure about compatibility. You have to look at certain conditions that would exist as far as installation. I believe if you were to have any questions on this exam dealing with field bus, I think they would relate to foundation field bus, because that's the most generally accepted and recognized standard by ISA. So I would focus on that, on the time spent on that. Let's look a little bit at foundation field bus control system. Well, you can use open software. That's your HMI. You can pick out what you want. You can pick out your human-machine interface, computers, what you're going to use. It's very flexible on that. And then, thanks to high-speed Ethernet, we can have a nice open standard network that works in conjunction with linking devices and different types of functions and control functions that we have, that gives us flexibility on our configuration and allows different people to use various devices once they're approved and checked to function with foundation field bus. In the field, you have the H1 network, and you have the foundation field bus interoperability, open standard, so that you can use many different types of transmitters, controllers, IPs, different types of equipment. And again, by using the foundation field bus, getting that information back into the control function, you can save a tremendous amount of wiring. You can actually, if you want to, also we mentioned earlier, you can truly move the control right out to these locations. But in any event, this is the basic foundation field bus control system that might get some sort of question on the exam. So the field bus standard foundation physical layer, you have the protocol for process control, then the foundation field function block language to configure. Many standard function blocks, different manufacturers have specific function blocks, but you basically configure using the function block approach to that, and then using the high-speed Ethernet network, you get the data exchange and connectivity. So this has become one of the leaders, I think, foundation field bus, and made possible primarily are locked by high-speed Ethernet, HSE. Using the Ethernet, based on the Ethernet with the Internet Protocol or the Transmission Control Protocol or use a datagram protocol, these have all been able to allow us to have systems like we're now looking at and with the Foundation Field Bus system. Linking devices, Ethernet devices, gateway devices, host devices, all put together basically give you the advantages and gives you the operation of the Foundation Field Bus. Open systems is a term used to mean very little other than connection to foreign devices. In fact, it was mainly a buzzword. But again, what has happened now with the Ethernet and the TCP/IP, the Transmission Control Protocol, Internet Protocol, has helped us set up standards. Now, the definitions are still changing, and there's some things go on different all the time, but this revolution has come about fueled a lot by the OSI 7-layer model that has different layers that connect the different parts of what you're dealing with as far as information transfer. One of the gentlemen that worked on some of the review courses that we've had does give this website here as a primer on layered communication. So you can go to that website and find out more information about the 7-layer model. You can find out more information about TCP and IP, and again, that may be part of the protocol discussions could enter into the signals and transmission and networking portion of the exam. So that might be something that you would want to dig a little bit deeper into as far as your study is concerned. Open systems today, they're being designed for easy interconnection, and again using the Ethernet and the TCP/IP based for transmission of data in blocks and chunks back and forth, and using machines as bridge and moving data around. And that's enabled now with equipment being approved to be used with a certain field bus system, and this type of communication has greatly opened up how business is being done today. Of course, we're moving even further all the time. We'll be moving toward disconnecting hardware from the vendor software and services, and you can upgrade hardware at lower cost and all the advantages. And as you can see, Field Bus has a potential radically change of our programmable automation control, our distributed control systems, whatever you want to call it as far as that's concerned. All of this type of work is moved rapidly and recently, and is changing almost on a daily basis. Pictorially, or this is sort of what we're talking about there, and again there could be some questions here. We're looking at 3 process areas. One of them may be the line chem, one the recovery boiler, one the paper machine, really whatever. And these have many different types of devices. Transmitters and valves are located all throughout these areas. And these devices are wired to, or hung off of, if you will, the field bus cable, which then is brought inside, and in there is the location. In this particular case, we have not used the control out in the individual smart devices, but we have our processing units located here. That's our controllers. That's where we've configured the actual functions of the information coming in, and where our controller outputs go back out to the area 1, 2, and 3. And then, of course, we have all of that tied to the HMI in the control room, where our operators are, and where we get into building graphics and our displays and this type of thing. So that's one type of configuration of many different types that you can have, but that's a conventional type, savings in wiring and I/O hardware, and you can actually go further with that, of course, by putting that control function actually in the field. So Field Bus today is a lot of different people moving in this area, multiple vendors. I believe you'll probably see a question or so on the exam dealing with that. You probably need to look at Standard 50, ISA Standard 50 and see what's available today, and then of course work on some practice problems and all that you might have. Okay, one thing I'd like to do at this point too, I was about to forget this, but I'm going to give you my email address, gwillbank@aol.com. Now, if you will email me, the first session we offered a summary of equations, and we offered a little bibliography listing of reference documents that people had found useful for the Control Systems PE exam. I can still offer to send that to you if you'll send me an email, but today what I'm primarily offering is a sample problems number 1. This is a set of sample problems that if you'll send me an email request, I will send you the sample problems and solutions, and you can use your summary of equations. You can use your own file of information and data. You can use whatever source you'd like to. It'll give you an opportunity to practice solving some of the problems that are similar to the exam. So I'll offer that to you. So while you record that down, let's review some of our key points. We've got to look at installation and how we wire and tube. I'm told that many of the problems on the exam will be very practical problems. There'll be theoretical problems, of course, but most of them will be practical application type problems. They'll be using some of the normal installation methods and what is the best way to configure certain instrument and control functions. We need to keep in mind about air. There are standards on that. Also, field bus developments, okay, that can be taken into account. And then the fact about smart transmitters and microprocessors have changed the current practice of how we do a lot of our work. Now, I think it's very important to keep in mind that on future seminars, we'll also be talking about, as I said, hazardous locations. We'll be talking about wiring practices, intrinsically safe, non-incentive functions, and others that are actually part of the wiring, are actually part of the transmission world, but we're covered in different sections. So today we've covered this part, and again, you have my email address, sample problem set number 1, or if you did not get and would like to have the summary of equations as well as a bibliography listing, I'll be glad to send that to you also. Okay, we're going to pause right now for another question and answer session, and then we're going to come back and after we do a little poll work, see how many people are at which location. We're going to look at some sample questions. So Alicia, if you will, would you mind checking now to see if we have any questions?
If you would like to ask a question, please press star, then the number 1 on your telephone keypad. Once again, that's star 1 to ask a question. We have a question from the line of Charles Nielsen.
Yes, go ahead, Charles.
Okay, I just at the end of the previous session, right at the very end, I hit the button. It really wasn't a question as much as a comment. One of the things that I used to use when I taught a lot of operators at the power plant about the difference between gauge and atmospheric pressures, I used to remind them if you picked up a gauge off of your desk, it's 0. You just remember to add 14.7, you got PSIA. This is a quick rule of thumb, a visual for people in their minds, but that was all that was really about earlier. I didn't really have a question. Sorry.
Yeah, that's very good. That's practically what you run into, and it's something that we need to understand is one of our bases for some type of a question that might be asked. Thank you very much for that, Charles.
Thank you.
Once again, if you have a question, please press star, then the number 1 on your telephone keypad at this time. Mr. Wilbanks, there are no questions.
Okay, thank you very much, and we'll proceed now. I'd like to, if you would, we need to get a feel for how many people are at your side. If you could fill in this poll slide, it would be good, and just sort of let us know how many people were viewing from your particular location. We have some that are multiple people, some that are individuals, and we like to get that record so we'll have an idea from future situations. Okay, I think we just about have the ones indicated there that we're involved with. Thank you very much and for that information and that input. And now let's take a look at a few sort of sample questions that could get involved in, at least it'll give you a feel for the type of questions that you might have. Some of the questions may be straight knowledge-based questions. For instance, this is number one. In an area of high electromagnetic disturbances, the computer data transmission medium with the least noise pickup is A, fiber optics, B, twisted pairs of copper with shielding, C, twisted pairs of copper conductors and conduit, or D, coaxial cable. And different ones of you may have some thoughts on that, or you may have books, and sometimes some of these answers can be a little bit tricky. And I would always remind you, always read and look at the question very closely. Look for the absolutes. In this case, it just says the medium with the least noise pickup. So you're wanting one, maybe it's least noise pickup, and the answer that my information shows that A, fiber optics would be the proper one there. Now keep in mind, sometimes you may have a preference or you may have a practice within your particular area or plant or facility that might operate differently. Always answer the question according to the general established and accepted standard situation. In other words, don't answer what you would do at plant A or B, but answer what you would do as far as general is concerned. So some questions will be a situation of general knowledge. Number two, the output from a pressure transmitter is connected to a field junction box with twisted shielded pair of 18 wires, number 18 wires. The same wiring is used to connect the junction box to a termination in the control room. The shield is attached to a ground connection in the control room and tied to the transmitter shield at the junction box. The shield at the transmitter should be connected to a ground at the transmitter, pulled back and taped at the transmitter, tied to the power cable shield, or terminated with a field ground rod. Again, that's one that you should read. You should take it into account, read what it's saying. You may have a reference to look that up in. You may just know this. You may understand this. And you just need to take your time. You have 6 minutes per problem. Some of these will be low-hanging fruit, and then you can just zap it out real quick, and other times maybe a little bit more difficult. In this particular case, the answer would be pulled back and taped at the transmitter. You don't want to ground the signal cable at both ends because you might have ground loops set up. We had that, I think, on one of the slides, and would be an example of the type of question that could be asked. Number three, approximately what is the pressure in PSIG on the bottom of a 20-foot tall tank filled with a fluid that has a specific gravity of 1.5? Is it 8.7, 12.99, 5.32, or 30? Again, a good example of a couple of items on our test-taking tips. The first one is read, read, read. Understand the question. Look at it. Visualize it. We have a 20-foot tall tank, and it's full. It says filled with a fluid that has a gravity of 1.5. And think back, and we're looking for the pressure, and this is very important. Watch your units. We want it in PSIG. And so I'm letting you sit there and look at this and say, what would be the first thing that I would do to solve this problem? Well, you remember I said the specific gravity is super important. And here we have 20 feet of liquid head, but it's also equal to, it's 1.5 specific gravity, so that's going to give me 30. 20 feet times 1.5 is 30. Well, look, I have an answer D. I could just jump down and say, well, that's easy. The answer is 30. Watch your units, units, units. What I have at this location is 30 feet. 30 feet. I don't have a situation of, I got 30 feet of water. I've converted that to the equivalent head of water. I have 30 feet of water. So now, what do I have to do? I want to get it to what units, PSI? I will have to say 30 feet of water, 30 feet of water. And I'm going to have a conversion factor. I happen to know that every foot that there is 0.433, okay, pounds, if you will, per foot of water. And if I multiply that out, I get 12.99, and that will be pounds per square foot. If you watch your units and do it properly, you will get an answer B, 12.99, and that is in PSIG. But you've got to, you've got to keep your units correct. I had 30 feet of water, and it's 0.433. Actually, that's PSI per foot of water. I guess I should have made that PSI. 0.433 pounds per square inch per foot of water. So if I got 30 feet, I have 12.99. So the answer is 12.99. People ask me, say, they'll have a lot of the distractors will be based on an answer if you leave out a factor. And that's what they did here. They put the 30 in there. So you have to look, make sure you keep your units proper, make sure you use the proper conversion units, and you'll be okay. So be aware of that. Sample exam question number 4. Which of the following practices is important in routing should have been fiber optic cable. It's like we got a word left out up in this portion right here. Should have been fiber optic cable. I'm sorry, I've got a little typo there. A, laying cable in trays with high horsepower motor wiring should be avoided. B, conduit fittings that require small radius bends should be avoided. Overhead runs on messenger wires should be limited to 75 feet. Or underground fiber optic runs must be covered with concrete. 2 or 3 points here. Probably they should have been the word most important, maybe most should have been in front of important, and fiber optic cable. So we got a little typos, but the other thing to look for, I'd like you to notice, look for absolutes. Must. Fiber optic runs must be covered with concrete. Now that can be compared to should, and that just means, well, that's a good practice or something like that. But if you look at these, and up here we also say should be avoided, and statements. So the statements may not all be false. They may not all be incorrect, but we're looking for the most important situation. In fiber optics, one of the main things that you definitely got to avoid is tight radius, small radius bends, because you can break the fibers. So we certainly would want that to be our answer B. The questions that I will send you, if you send me an email, will have questions like this. It'll have some calculation questions. I think it'll be good for you, so I invite you to send me the email situation there, and I will send that information back to you. One of the things is studying in other types of information. There's some different books and all, different classes. Here's a couple of classes ISA has dealing with process measurement and control, and also pressure and level measurement engineering. Of course, we've talked about some other references time to time too. A good study book being the Bell Liptak book, but also the Tika book as well as the Byron Lewis book that you have on your bibliographies that most of you already have. But anyway, find other sources for your study. Look at transmitters, look at pressure measurements, look at wiring, look at connections, look at all different types. And I would like to remind you that ISA does have a couple of certifications, the Certified Automation Professional, Certified Control Systems Technician, that are available to you. But thank you very much for participating. I hope you benefited from this, and I look forward to our future time together. And thank you very much. And now, Alicia, I'll turn it back to you to remind them about the seminar survey.
This concludes today's ISA web seminar. Please do not forget to fill out the evaluation survey found in your email inbox. Thank you for attending, and have a nice day.